The last family of models or recurrent neural network models we'll work with are the bidirectional RNNs and the deep RNNs. Throughout this section, we've been used to working with RNNs such that the hidden states, or in some cases the hidden and the memory states, are being propagated from the start to the end. So normally we used to have an initial hidden state, initial memory state, and then after doing some computation in this box, we kind of like propagate this to the next, and so on and so forth throughout the sequence length. And this works just fine for sequence models, as what happens in the future depends on what happened in the past. But now, we also know that in many cases, what happens in the past, that's so-called past, actually also depends on what will happen in the future. So it's also very interesting to propagate the states in the backward direction. So for many tasks, this happens to produce better results, because many times the starting and the ending points of the data are interrelated. So this is what does bidirectional models look like. We now have to back propagate this. So instead of just forward propagating, now we could also back propagate. And then the other type of neural or recurrent neural network are the deep RNNs. Now in this case, we've used the bidirectionals to explain the deep RNNs, but we could also use simple RNNs like the simple GRU, which is not bidirectional, to explain this. So the deep RNN, as we could see clearly from here, is gotten by stacking up RNNs on top of each other. So with this, for example, suppose we have an input right here, we get the output, and this output is used as the input in the next RNN layer, and this is used as input in the next RNN layer for as many layers as you want. And this happens also to have greater results compared to the very simple models, although it's computationally more expensive. Working with bidirectional RNNs is made quite easy with TensorFlow. What you need to do right here is just to include or pass the recurrent neural network as a parameter to the bidirectional layer. So here we have bidirectional of this, and there we go. So let's include this right here. We have bidirectional, run this. So we could test this and see the output we get. We see how instead of getting the output we had before, we now have instead 2 times this number of units we have stated earlier, and that's because we have 2 hidden states at every time step. So let's take this off. Let's have this. Okay, let's call this layer 1 and layer 2. So we have this layer 1 without the bidirectional, and then layer 2 with the bidirectional. Run this. So there we go, we have layer 1. Okay, run it. We'll see the output. We'll see that we have the number of units 40. And now if we consider in layer 2, the number of units goes to 80, and that shows us clearly that we're having to do with a bidirectional RNN instead of just a simple RNN. Now let's modify this model which we had previously. So we could have this, we have bidirectional of this. We'll take this off, it's been defined already. So we could have this, even this, we could take this off. So we have the dance, reshape, and dance. Okay, so this off. Let's reshape. So that's fine. Now we come back to our model. We run this. We recompile our model. and then we train the model. After training for over 10 epochs, we see how the loss decreases both in the training and validation sets, and the accuracies also increase. Although the highest accuracy we obtained for now is 79.88%, which is similar to what we obtained in the unidirectional recurrent neural networks. So let's print this out. And there we go. We could continue training also to see if we could get better results for the validation set. But obviously for the train set, we will always continue to increase in accuracy.